Only 4 students today. Okay, for who just entered a Zoom meeting here, use the Piazza, use the link on Piazza to get access to today's discussion material. It should be a link to a Dropbox, and it's in the week 2 folder. The name of the file is discussion 4. Okay. Does everyone get access to today's discussion material? Okay. So cool. Before we start, are there any questions in terms of homework and are there any questions in terms of the homework and the incoming quiz, the scope of the incoming quiz on Friday? If you have any question, you can either put it in the chat room or raise your hand. I'll mute you and you can just go ahead. Yes, you're supposed to write a pseudocode. Actually, there are description. I'm not sure because I just finished the quiz. I just finished looking at the quiz, and it's basically most of the questions are about designing algorithm. And I think if you use description, sometimes it would be really hard to express your whole ideas, your whole thought process. So maybe pseudocode, and the pseudocode doesn't have to be very complex or very. I mean, you can use functions and pseudocode plus its description, but I would definitely recommend using pseudocode. Okay. Okay, so we have 8 today. So for the student who just came in, use the link on the Piazza to get access to the discussion material. I'll just copy, I'll just paste yeah. No problem. If you use Python, then it's actually better because, I mean, the Python using actual code is more is definitely better. So Python is definitely accepted. Okay, let's get started. So let's take a look at today's first question. It's actually a very classic question in terms of depth first search algorithm, which is the first question is about the application of depth first search algorithm on different data structure. So I'll give you guys around 3 to 5 minutes to take a look at the question while I set up the device here. Set up my device. Yeah, it's discussion 4 PDF file in the week 2 folder. It's in there's a link on Piazza that has all the materials about the discussion session. It should be the first post, and there's a link to the discussion material. Yeah, and also you can use that link too. You can find all the the recording materials and the discussion materials on that post. Okay, the deep copy means like there's like a shallow copy or a deep copy. Deep copy means we want to completely copy the information in this list because like there are pointers in linked list. So when we do a deep copy, the address that the copied version of the linked list, like the address that the copied version, I mean, the pointer of the copied version will point to actually the copied node instead of the original node. So that's basically deep copy. So if for this question, if let me show you, if this is the original node here, 1, 2, and a deep copy basically means we have another 1' and 2' and points to now. This is a deep copy. Just everything is completely copied from the original node. Because since this is, there are pointers in here and pointers will point to the address of the node. So like deep copy will basically means the pointer in the copied version will point to the copied node. Okay, I think most of you guys have already looked at the question. This is basically an application of depth first search algorithm on different data structures. Because like for depth first search, it mainly applied on graph, but there are different representation of graph in real-time scenarios. And in your homework, you actually encounter like another representation of graph, which is like a 2D plane. I think it's question number 5 about the Mario question. So for this question, the graph is like another representation. You need to, like when we're trying to apply like graph algorithm on like another form of data structure, it can be array or linked list in this question. We need to first figure out what are the vertices and what are the edges. And for this question, the vertices and edges is quite obvious because like as you can see, these nodes, these linked list nodes are actually vertices, and the connection between these nodes, these like next pointers, the connection between this and this random pointer are actually the edges. So the only problem right now, we now identify what are the edges and what are the vertices. The next step is to figure out so what kind of modification should we make on the original depth first search algorithm so that we can solve this problem. So for the original depth first search, we need like a visited array that basically marked what nodes we have already visited or not. And so for this question, we not only need like a visited array, we need like to copy the original node. So that leads us to use like a newer, like another data structure to store the information, to not only store what are the nodes that in the linked list that we've already visited, but also store the copied version of the original node. So that leads us to use like a dictionary. I'll just write it here. We'll just use dictionary here to store the information. The key will be, key is the original node. And the value is the copied version. And to represent the key, I will just use this to represent to represent key value pairs. And so let's get started with our DFS algorithm. So let's start with this node first. And for this node, when we first encounter this node, the depth first search, in the depth first search, we'll first try to check whether this original node, whether we have visited this original node in the map we have, in a dictionary we have like design we were created before. And since like we haven't visited one before, so we first create a copy of it. Let's call it 1 prime here. And we'll only like copy the information of just copy the value of it. We will not copy the information of the next pointer and the random pointer of it, because if we copy the original information, then like the address of this pointer will actually point to the original, like the original 2. And what we want the next pointer of 1 prime points to is the copied version of 2. So we will not copy when we made a copy of the original node, we will not copy the pointer information. And right now we copied this and we put it in the map. Let's call it 1 to 1 prime. And right now we want to traverse all the outgoing edges from node 1. This is the first outgoing edge. So let's just go here. And we encounter 2 here. We haven't visited 2, so why not we just make another copy of it. And then after that, we recursively call that first search algorithm. Go here. And we encounter 3. And we haven't visited 3 before, so as usual, just made a copy of it. Let's call it 2 prime and 3 prime here. And then from 3, we first encounter this now. And there's only one now in the system, since now means the object doesn't exist. So when we encounter now, we just return now. And now is here. And we return it now. So the next pointer of the 3 prime will point to now, because that's what we return from the recursive function here. And then we want to visit this edge, the random pointer of 3, the original node 3, and this is where we go. And we see 2. 2 has already been visited, since like we have the key of 2 in our dictionary. So we will just return the copied version of 2, which is 2 prime here. And we will, since we return 2 prime, so the random pointer of 3 prime will point to 2 prime here. And now we're done with node with value 3. And then we go back to node with value 2. Since we finished everything with node of value 3, we will return 3 prime to the function to the the function that calls the DFS algorithm, which is, since we called 3 at a node 2. Yeah. This is just a drawing problem, I think. 3 prime actually not point to the pointer of 2 prime, point to 2 prime. Let me just write it more clearly, point to 2 prime. Okay, and since we returned 3 prime to the previous recursive call, just the next pointer of the 2 prime will point to 3 prime. Yep, and then we traverse the random pointer, not traverse, visit this edge here, and which will lead us to now. And if we encounter now, we just return now. Yes, yeah. It's definitely for a linked list that does not contain duplicates, or also like the duplicate of value actually is accepted, since like I mean the duplicate of values is okay, because when we're using map, we're not using the value of the list node as a key, to perform the hash function. We actually use the address of the, I mean, we're using the address of the node, the object in the in the algorithm to perform hash function. So like, yeah, even if there are 2 nodes with the same value, I think it will have like different hash values. So we'll have like a different copy, even although like the value is the same. Okay, let's continue. And where we're at? Yeah, okay, we're done with. I'm sorry, we're done with 3, and here we just. Oh, sorry, we'll point to now. And then after we are done with 2, just go back, and since 1 caught like the DFS on 2, so the next pointer of 1 prime will point to 2 prime. And finally, we just want to visit this random pointer here. And 3 has already been visited, so we just return 3 prime here. And then finally, we just return the address of 1 prime, and we finally get like a deep copy of the original linked list. Yeah. So there's actually another follow-up question for this. And the follow-up question will actually, since like, yeah, let's first like discuss the running time, the time complexity. Time complexity, since this is that first search algorithm, so time complexity, E plus E. And since this is an edge, there are only like 2, for each node, there are a maximum number of like 2 edges for each node. So the number of edges is actually 2 times V. So the running time of this is O2 times V, which is O of V. And the space complexity is definitely O of V, because we store like a key value pair for each node. And so I will like give you guys some like a follow-up question. I will not cover during the discussion session, but you guys are very welcome to discuss during the office hour. Like, is there a way to perform this deep copy with no extra space, that we do not use this map to perform this deep copy? And try to think about it, and if you have any ideas about that, we can discuss it during the office hour. Okay, let's take a look at the second question. Second question is like quite easy, I think. Just a basic review of detecting detecting a cycle in a DAG. I'll just give you guys 1 or 2 minutes to figure that out. Quite simple. And since I think during the lecture, the professor used pre and post numbers to detect the back edge. But if we just simply want to detect whether there's a cycle, there's an easier version of that, easier way of doing that. Random pointer. The one random pointer of the random pointer of 1' will point to. Simon, if we can discuss it later after this discussion session. I didn't quite follow your question. Okay, let's take a look at the second question here, which is detecting a DAG in this, detecting a cycle in a directed graph, not a DAG. I'm sorry. Detect a whether there's a cycle in a directed graph. So the approach is we want to find the suspicious vertices, and then we want to check whether that vertices whether there's a cycle contained using depth first search. And for the reachability problem, we just use whether a node has been visited or not to mark each node. And right now we want to add another status for each of the node that has been visited. So let's take a look at the following example. Very simple DAG. If we just apply the whether a node has been visited or not, we cannot detect whether there's a cycle, because if you just apply the function, you'll find that out. And right now we want to introduce a new status on all the nodes. So it's very similar to the pre and post number of that first search tree. But let me just show you guys. For status new, that means unvisited. For a visiting node, that means that the DFS already started on this node and has not finished yet. DFS started, not finished. And finally, visited. That means basically the DFS has already done with this node. And so I just write down some simple pseudocode here. The status is an array. For all the nodes, and it is and the status array is initialized as new for all the nodes. So when we visited our vertex V, we just mark it as visiting. Then we have already started a DFS on this node here. And we traverse all the outgoing, all its neighbors. If the status of the neighbor is also visiting, then we'll just directly return false. Because basically that means we already detected a cycle, because that means the neighbor the depth first search algorithm applied on its neighbor has not finished yet, and that means we actually come from the neighbor that started that first search. So we'll just directly return false here. And then if status W is true, is new, then we apply the DFS. I'll just write DFS here. DFS WG. And we just recursively call this function. And if there's a cycle in its children, we also return false. Otherwise, we mark, after we traverse all the neighbors, we mark this node as visited. And then we return true. So this is basically the depth first search function. And since like in the question doesn't mention about whether all the nodes are connected or not, so we need to have an outer function that traverse all the nodes and call this depth first search function to make sure that there isn't a cycle in any one of the component in this directed graph. So let's just just a review of the lecture materials here. Yeah, it's cyclic DFS. I'm sorry. Just this is the same. Okay. And let's move on with the next question. Next question is actually a very interesting question. It's basically about using depth first search tree. So the next question is, we want to find like the critical connection in the graph, and I'll just basically explain what is a critical connection. And for this problem, the representation of a graph is different. We will use like list of edges to represent the whole graph, and we guarantee that all the nodes are actually connected. So there's actually an edge between any one of the node in this graph. And so if you want to perform any kind of algorithm, you need to transform this list of edges to adjacency list. That's probably the first step you want to do. And about the critical connection, let me just briefly explain what is a critical connection. So if we look at this graph, this simple graph here, and if we remove this edge or this edge or this edge, the graph will still remain fully connected. All the nodes are still connected with each other. But if we remove this edge here, then 3 will be separated from the whole graph. And this is actually the critical connection in this graph. And what we want to do is to find all the critical connections in this graph. So I'll just again give you guys another 3 to 5 minutes to think about this question. Good question. Runtime limit. Usually I don't Yes, yes, that's a very intuitive way of doing that, but could you figure out a better way, a better algorithm? Because that seems like a O n square algorithm to me, and that's like the first intuitive way of solving this problem. There's no runtime limit, just find the best solution, the best option, the best algorithm you have. You can figure it out. The number of children. No, for this question, I think the input is only the number of nodes, number of total nodes in this graph and all the edges in this graph. So the first thing you need to do is to transform this to adjacency list. And if adjacency list, then the size of the list is actually the number of neighbors. I think that's what you mean. Yeah, you're getting there. Yeah, it's actually like the idea is correct, but the answer is like the question is how can we get all the edges that might not like that is not involved in the cycle. Because like the hint is used that like you can think of like the pre and post numbers in the lecture and try to apply something similar. The hint is using depth first search tree. Yeah. Okay. I think probably you guys already have like a general idea about this question. So Simon mentions one of the possibility of one of the algorithm to solve this question, which is basically like a brute force way of solving this problem. We just I don't know why like I have to reshare the screen. Just one sec. Okay, so Simon mentions like one of the ways to solving this problem, which is we just remove one of these edges one by one. So for example, we just first remove this edge and apply the DFS algorithm to see whether all the nodes are still connected or not. And we do that repeatedly for all the edges. And if we remove, so for example, if we remove this edge and all the nodes are not connected, then this is definitely the critical edge. But like the technical complexity of this problem is like this. Since we have E edges, and for each DFS algorithm, it will be V plus E time complexity. So if the brute force, the runtime of the brute force algorithm is actually this. Yes, you can do that. But like, I can't give you like a counter example, but like that will not solve the problem. And we want to find all the edges here. And so the way we want to solve this problem is actually like this. We want to, what we want to do is to, yeah, it's similar to MetaGraph, but yeah, it's very similar to MetaGraph. And the way we solve this question is use like, it's basically the augmentation of the depth first search algorithm we used before. Let me just briefly show you guys the ideas. Suppose like there's an edge. Let me just write it here. Suppose there's an edge U2V here, and if this is critical, then what that means? That means like U, as first we assume that U is the V, U is the parent of V in the depth first search tree, and if this edge is critical, that means there does not exist any alternative route to reach U or the ancestor of U from V or the subtree of V. That might seem a little bit like hard to understand because things, this is an undirected graph, but we want to transform this undirected graph to a depth first search tree, which will be like kind of like a directed graph. And let me just repeat what I just said. We want to ensure that there is no alternative for V and the subtree of V to reach U or the alternatives of all the ancestors of U. I'll just like use an example, go through the algorithm step by step to show you guys how this thing works. So similar to the pre and post, we will have like two array here. First one we call it distance array, and second we call it the lowest array. The distance array is basically the time that the depth first search algorithm reach the node. So for 0 node, and we will initialize them as -1, which means like, which basically this means that this first node, the second node, the third node, and fourth node, we haven't visited any one of the nodes in this graph. And the low, the second array low, we'll initialize them as 0, basically means the lowest level that this node can reach in this depth first search tree. Remember, like depth first search tree is different from the undirected graph that we have. And let me just go through this algorithm. I think you will get the idea. So first we start with 0 here. And since this is the first time we encounter 0, this is -1, the first time we encounter 0. So we will initialize the distance as 0 and the low as 0. This low is basically means that the lowest level that the 0 can reach in this depth first search tree is 0, which is itself. And we update the value here. And then we continue the depth first search algorithm. We visit 1. And 1 we haven't visited yet since this is a -1. There's a -1 here. So the same, we just initialize the distance. The distance basically the time that the DFS algorithm reached this node. And then the low as 1. We initialize low the same as itself. And we update the value here. And then we visit 2. Same before. Let me just mark this. This is the direction of the depth first search tree. We mark this as 2. and the low as 2 as well. And this has already been visited yet. So we update the value here. Distance is 2 and low is also 2. And here comes the fun part of it. And for 2, since this is like a depth first search tree algorithm, so for this algorithm, we will not revisit the parent in this depth first search tree, which is 1. So for 2, there are only 2 edges here, and this is its parent, so we will not visit. And this is another one. This is another edge, so we will visit this edge here. But we've already seen that 0 has already been visited yet, so we will update the lowest level that this node can reach in a DFS tree based on its neighbors, if that neighbor has already been visited yet. Since this is the lowest level that this node can reach, 0, that means the lowest level that 2 can also reach is also 0. So we update this value here. This is now 0. And since and then this edge will actually be like a back edge in a depth first search tree. And this is not the edge that we want, because the definition of critical edge, I've already mentioned that if we disconnect it, then we will lose the connectivity between all the nodes. So this is definitely not what we want. And then we go back to 1. And from 1, we get the information returned from 2, and we see that the lowest level that 2 can actually reach is actually 0 here. That means the lowest level that 1 can reach in this depth first search tree is also 0, because because 2 is my subchildren, and if there is a way that 2 can reach 0, then definitely I can reach 0 as well. So update that to 0. And since this 0 is larger than 2, that means the lowest level that 1 can reach is actually larger than the time that 2 got visited. So definitely there is a kind of cycle in this whole component here. And then this is not the edge that we want. No, I mean the 2, the first number here, this is the time that the depth first search algorithm visit to, and the second number in red is actually the lowest level that this 2 can reach in the depth first search tree. This is the depth first search tree. For now, this is the depth first search tree. The level from here, the level here is 1. I'll mark it in 1, 0, 1, 2. And in this depth first search tree, the lowest level that 2 can reach is 0, because there's an edge here. And we update this low here based on this edge. That's why we update 2 to be 0. And since 2 is the children of 1 in the depth first search tree, then if there's a pass from 2 to 0, then definitely 1 can also reach 0 as well. And that basically means these 2 nodes are not the nodes that we want, since there's a kind of cycle in this undirected graph. And right now we finish all the nodes here, and let's try and traverse this pass here. Go from here. Lowest level here. Okay, so basically this is a tree, right? Let me just move on here. I'll explain it. If this is a tree of a depth first search tree with 4 nodes. If I write it this way, this is like a tree. So this is level 0. This is level 1. It's not level, it's like since the level here is not like the level of the tree, it's based on the time that the depth first search algorithm reach the node, and that we will call this level. We will just define this term as level, and this is the second node that we reach, so it is 1. This is third node that we reach, so this is 2, and this is the fourth node that we reach, which is 3 here. And right now we're at 3 here. And for 3, we will just initialize, since this is I think the fourth node that we already visited in the step first search algorithm. So we'll mark this distance as 3. And when we first encounter a node, we initialize the lowest level that it can reach as itself. So this is 3 as well. And since there are no other outgoing edges from here, we will just return back to 1. And from 1's perspective, node 3 is actually its child, and the lowest level that 3 can reach is larger than the level that 1 at. So that means like there are no alternative route from 3 to go from 3. Let me just write it here. From 3 to go back to like the earlier nodes, which are the ancestors of 1. There are no this kind of back edges here, since the lowest level that 3 can reach is larger than 1. So this is basically why this edge will be selected as a critical connection, which is the answer to the question. Okay. So there must be a connection. There doesn't have to be. For example, like 3, since 3 is the lowest level, 3 is the last. 3 is the last element we visited in the step first search, so there is no connection to the lowest level for that node. This is like basically like a leaf in the step first search tree. Yeah, and like after this, I see time's up, and so I'll stay here for another around 5 minutes, and I'll upload all the codes about today's discussion materials in the folder as well. So you can look at the Python code and figure out this question later. And if you guys have any questions, like come to tomorrow office hour to discuss it. So if you guys have any other questions, you can jump on mic.